Start recording. So we are recording the session right now. Let's take a look at what's due. We're going to do a question and answer today, but what is coming up shows over on the calendar right here. Due date and due date. PO is probably portfolio. I don't know why that other one shows up. I don't know what's up with that. Let's take a look at it. And it says that, oh my gosh, it doesn't have everything on it. This is your everything one. My gosh, this is the full one is due. I guess I didn't update that one. Let me go ahead and do that right now. Is your rated submittal for unit 4, 4.1, 4.2, and 4.3. Here we go. So this is your, I'm pretty sure that's right, because we've already done the partial one. So if we look at that, that's coming up. That's on the 18th, which is Sunday. And so 4.1, 4.2, and 4.3. And we've talked about 4.1, 4.2 a lot. We've done a little bit of work on 4.3. And remember, 4.3 used eQuest. And I showed you yesterday, or on Tuesday, how eQuest works. There were some issues with it. I had to do a quick reinstall. It really didn't like being on my D drive. So I put it back on my C drive, and it seems to be much happier. Sometimes the older programs do that. They have hard links as to where things are saved and stuff instead of relative paths. So those of you who are into programming, I learned to program on a Burroughs B6700 in the bottom of Hutchinson Hall at UC Davis, and we punched cards. That's how I learned to program, punching cards. And then in my senior year, this very cool thing appeared down there. It was called a terminal. And we could actually type on the terminal instead of the card puncher. So that's kind of showing you where I came up from, right? And I learned Fortran. I don't think Fortran has existed for 40 years now. So anyway, 30 years at least. So those of you who are into programming will know that where you store things and hard paths versus relative paths are pretty important. But let's take a look at 4.3 again, because I went over sort of how eQuest works, and I redid a demonstration yesterday that is a little more coherent than what was in the lecture. So you can look at that. It's actually not needed. You don't need in this class to know how eQuest works. But I really think it's good to have that background knowledge. You won't get tested on it. It's not part of a requirement, but I think it's good to kind of see, first of all, how complex an energy analysis is and all the pieces that go into it, and to know that we do have really good tools for figuring out energy. We are no longer guessing. We just don't guess anymore. So the next thing, though, is with all this data coming at us, how do we make sense of it? And the ability to review data and draw a conclusion is really, it's hard. It's one of the harder things that we've got to do. And so I'm doing something that's called the most basic analysis that we can get. It's from Descartes. He set up this system, Cartesian logic. And that was in the early 1600s. Descartes was pretty cool. He really had his act together. They say that he codified, he didn't invent it, but he codified and wrote in very convincing and straightforward ways the scientific process, that we use now versus the correlative process, which was used before. Now, the correlative process is very strong and it's very good, and the two are starting to merge now with the ability to correlate so many things, which is one of the things that AI does. It works on a correlative system of recognition of like parts. And in part, that's one of the things it does. So they're coming together, but I want you to be able to take these very basic steps. And you've heard the term QED, which is sort of like, if you want to translate it into English, some people call it quite easily deduced, but it's quorum est deductum, which means you can't break it down any more simply than this. It's down to its basic form, and you just got to be able to look at it and see. That's what QED, I think, I don't know, I'm not a Latin major, but quorum est deductum is you can't break it down any farther. And so that's what we want to do with that data. So let's take a look at, Nick, can I go ahead and share yours really quickly? Is that okay? Cool. And again, something else might come up, but 4.3, I'm going to look for, there it is right there. And I'm going to pull it up. And I pull it up, and so, oh, here it is. It downloads for me. And so this is a pretty nice way of presenting it. It is not the only way. But he's got the original statement. Here's an example how data can be used. Here's a view of the data. And he starts out, as I suggested, from the data I see. And then he makes the statement. Okay? And his statement is, from this data, 1, 2, 3, 4, that the roof type and the radiant barrier do not influence the energy cost significantly. And then he qualifies that because he knows that this applies to one building in one environment. So he says, in the current environment that this home is in. Okay, so he's making clear that his statements only apply to this one. And that's pretty important. If you try to generalize this statement, you would be wrong because you only have one set of data. If you had thousands or hundreds of thousands or millions of data sets like this, you could review it and find out if the data says that it's a general rule or not. Okay, and then the next thing, I also see. So that's what I suggested. From the data, I see that. I also see that. And then the only major influence is the reduction in the building pad area. The only thing, and I'm not going to ask you to redo it because you're sort of out of room. You used up all the room. You could say from lines 2, 3, 4, and 5, I see that. Instead of from the data, you could say from the data lines 2, 3, 4, 5. That would bring my eyes to those. And then you would say, and I also see that from line 6. But this is not a very big data set. And if I can't see that myself, I've probably got some issues of not being able to look at where I'm directed. So now there's 2 observations. And so he's making a conclusion placed in an environment where there is little drastic change in weather. And so all of these drastic things don't make a difference because of the weather. And so those would be unnecessary and they would be expensive, and you could use your um, money somewhere else. So this is a well done argument. If you took, I don't know, it's been so long, but in some English class they told you about argumentative essays and informational essays and all that kind of stuff. Um, this would be informational, but you are drawing a conclusion, right? That is telling somebody what they should do. So I call that a predictive argument. They don't talk about those things in English class, but when you get into science and engineering, that's called a predictive argument. There is a prediction here, and I'm going to follow that prediction. Okay, so because there's data. Anybody else got one that I'm going to stop sharing. Does anybody else have one that they want to put up? And we can look it over and look to see what parts are there and what, because that was not the only way for sure. That was a way. Does anybody else want to go ahead and do one? Kate or Abdul or Eric or Lena or Blake? Or you can just put a link in the text area and I'll pop it up and share it. Nobody gonna brave it out? Okay, so Eric says his isn't ready yet. Well, now you've got a model to work with, and you can use other models. Yeah. So there we go. Well, see, that's one of the problems with getting yours in early and not either having a lot of things to add or not having a lot of things to add. Okay. Well, so look, this is your chance to help really get it well done, because these are one of the toughest. This is actually hard work, and we don't teach it a lot, which is why I wanted to write the analysis based on the conclusion. What did I put in the modules? Did I do something a little bit, give you a little bit more information? Oh my gosh, here we go. Wow. Let's see what my no. So I didn't really give you a lot to go by. Okay, so let me do that here. I'm gonna add this onto this just so that you can see it, because I've told you, but I haven't really put it down. So that's your basic, and that's a little bit small, I bet. Oops, I got to be presenting over here now. I stopped presenting to let everybody else take their shot, and nobody took their shot. Anybody see Hamilton? Are you guys fans of Hamilton? Oops. Got to take my shot, not going to lose it. I thought that was an excellent. I saw it on Disney, right? I actually paid my $6 for a month of Disney, watched Hamilton, and then turned off my $6. Well worth $6 to see it. Okay, so here's what your analysis. I see that. I also see that. And from these two observations, I conclude that. So I'll give you another version of it. Let's see. Here's my data set. And this was a little bit about where I got it from, by the way. If you look down here, this was sort of, and here were some questions you could do. But let's take a look at this and see what else I might do. Okay. You might say from line 1, I see that a standard design would cost about $3,800 per year in energy-related costs. I see from line 2 that light adiabatic coloring saves $12 per year. From these observations, I conclude that color is not important for energy on this house, and I will allow the client to pick the color. Okay, so that might be a way of a totally different one, right? But it's, I see one thing, I see another thing, and then I go on. Okay, so let's take a look at another one that you could do. Okay, I see that advanced wood frame, or I see that from line number 3, my annual energy use will be about 18,840 kilowatt hours. And from line number 4, where I have added an additional R30 insulation, I still use about 18,840 kilowatt hours per year. From these observations, I conclude that there is a maximum amount of insulation that I will need to maximize this house. And then you can add one more thing. My next step is to find out how much insulation I really need. Okay? And you could go back, and that would set you up another study. So that's another part of a conclusion, is sometimes your conclusion says, and I need more information to get where I really want to go. Where you really want to go might be, how much insulation do I need? So when you do an analysis, which means to order your data in such a way that trends and patterns appear that help you solve problems. So I see a trend and a pattern, but it didn't solve the problem that maybe I'm most interested in, which is, how much insulation really do I need? Because, insulation costs money. Now, it could be that there's a standard to go by, and you just have to meet the standard. Most standards start with, in the absence of engineered analysis, do this. That's how most standards are. And so if you had an engineer that came in and said, I've engineered this building like this, and so in this case you could change that. Okay? But in this case you might say, well, I wonder how much insulation I really need. This did something. but I wonder what's in there already. And maybe that's enough, and maybe I can do less there and more here. So this didn't answer every question I might have, and you might add a question for further review on your conclusion. Okay? Conclude something, but say, didn't quite get to where I want to go. It's close. Okay? So that's 4.3. Let's come back to our home here and look at lecture. So this is now just a question and answer period. Does anybody have questions, or would they like me to review anything in particular on 4.1, 4.2, or 4.3? Yeah, so Eric says, I think you are pretty clear and you can go different ways on the information. That is absolutely right. Most data sets actually allow you to do that, which is why there's data is a very important part of science. But when you just try to analyze data without the question being involved, um, you get some difficulties. So, or if you analyze the data without applying basic principles. So, from this you might have to draw on some basic principles too. You sort of have to know a little bit about heat. Heat is the presence of energy in a material. Okay. We think of heat as, oh, it's hot, and we think of it as a relative thing. And you absolutely can do that. But in engineering terms, heat is a measure of a type of energy that is available within material. And so heat transfers in a couple of different ways. There's convection. There's now I'm just totally blanked out. I studied this for years. But there's basically by touch, by current, and by radiation. Okay, all three of those happen, and that's why they've started putting rad barriers on, radiation barriers. They actually keep the heat from releasing from the material. You go, why would you want to do that? Well, there are many times when you want the heat to stay in the material, okay, and to have some control over it. Anybody live on the East Coast for a period of time? Any of you East Coast people, particularly like Northeast, like from New York, Pennsylvania on up? Anybody know how one of the main ways that they keep buildings cool there? It's way different than here because they have lots of a material that we don't have. It's called water. Okay, so here's what's very common in much of New York is you have a water tank on top of the building, and that water tank is situated to soak up all of the energy. So instead of hitting the building and having the material that absorbs and then gives it off slowly, they have the water take it up. And then since water is a fairly good transfer, how do they get But more importantly, water is easy to dispose of. And so at the end of the day, when it's cooling off, where normally if all that energy got soaked into the walls and it starts radiating out of the walls, you go there and they just dump the water. They just dump the water down the drain. So they've protected the building. Yeah, yeah. The East Coast is way different. They also use what they call radiant heat in the floors. They do a lot of hot water, steam, or gas heat in the floors because you can pump it around and do things with it. And that's when you have wide variations in temperatures and things like that. Does anybody live in a house or an apartment or any kind of some sort of a structure where it's hot outside and it seems like you've kept the house pretty cool and it gets down to about 70 degrees outside, so great, I'm going to open the windows and turn off my air conditioner and your house heats up? Anybody have that happen? My house is like that. It's beautiful outside and I open the windows and my house heats up. What's with that? Anybody know why that one works? Anybody experienced that? Oh my gosh, I live in a Stanley Davis house. It's made that way. So your walls suck up the heat. They do. They're big, they're flat, they're right in the way of the sun, and they soak up the heat. Even if they're well insulated, they are sucking up the heat. It's not all reflecting and it's not all passing through. A lot of it is being built up in the walls. And so what happens if it gets cooler inside the house than the heat in the walls? Which way does heat go? It goes from hot to cold, just like water goes from high pressure to low pressure. Okay? Yeah. Oh my gosh, built in the 1890s. Yeah, that would really do it. And so what they do now is they actually put these radiation barriers on the Tyvek of the walls that you want the walls to suck up the heat and not go in if you can. But then you want the radiation to go outward, not inward. You want your house to remain cool like you've kept it cool with your air conditioning or your fans or whatever. So they put radiation barriers on the insulation, but you don't want to keep it all in, so you put it on one side, which is your inside your house, and you let the radiation go the other way. Now, if you live in an area that your hot and cold are sort of reversed for a major part of the year where it's more important, then you'll do it the other way. You'll keep it so that the energy in the walls actually radiates into the house to keep it warm because it's cooling off too much. So this energy stuff, man, I tell you, it's a big, 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 big deal. And if any of you have to pay for your energy rather than having it rolled into a rent or something like that, you know that energy prices are going up. And we need to conserve, and not just because the prices are going up, but because we do run into limits. Cool? So hopefully this clued you into that. All right, then, since there doesn't seem to be a massive amount of questions or need for review, I'm going to go ahead and stop the recording.